Okay, a lot of our goals in doing calculus are to find the best answer. Ideally, since this is a calculus class, this best refers somehow to the largest or smallest or most optimal solution. This process, therefore, is optimization. I want to find the best solution for the situation I'm in. Problems like this are thousands of years old. One of the oldest ones of these is a fairly simple question. I give you a bunch of spheres, and I want you to put them as close together as possible. I mean, think about it. I give you a box, say a cube, and I give you a bunch of spheres, and I say put as many spheres as possible in the box. Or I ask you to stack them in the way that is densest. Well, then I'm trying to minimize the amount of room used, or maximize the number of balls I can get in each box, right? Since I'm trying to find a maximum or a minimum, that is a calculus problem. That particular problem, by the way, the cannonball stacking problem, was known to Johannes Kepler back in the late 1600s and was known as the Kepler conjecture. And it was only proved that the optimal solution to stacking spheres as tightly together as possible is the way you see them in the grocery store. If you go to the grocery store, you see a pile of oranges. How are they stacked up? You get a row of oranges, and then you get another one. They sit in between the jumps, right? And then on top of those, you get one that sits in the little divot created by three of them, right? That was only proved to be the best possible arrangement in the 21st century. That was known in the 1600s and was proved to be the best 400 years by Dr. Alan Ho, professor of mathematics at University of Pittsburgh. Sorry, no, Tom Hales, University of Pittsburgh. Wrong person. Right idea, wrong person. The process is always the same. I need to read through, figure out what I'm trying to find the ideal setting for. Whether it's a maximum, whether it's a minimum, maybe I'll need to draw a crappy picture. Even a crappy picture helps. Then I decide on some variables and I try and create an equation that fits them. Just like with related rates, that's where the biggest stumbling block usually happens. What equation do I need? If I figure out what the equation is, then I can figure out how to put it in one variable and how to take a derivative and find a maximum or a minimum. So here is an example problem. Page 337. Well, that's the old book version. Problem number 12. I am going to make a box with an open top. I'm going to make this box by taking a piece of cardboard, cutting a corner away, and folding up the sides, thus giving me a box. Now, in particular, this is a bad example because this piece of cardboard is a rectangle, and it says here we're going to start with a square piece of cardboard 3 foot wide. So this is a bad image. Picture a square piece of cardboard. We're going to cut a notch out of each corner and fold up the result. I want the biggest box I can make. I want the box that holds the most stuff. Starting sheet is a square. I'm going to knock out something in each corner, and then I'm going to fold it up. So here's my square piece of, well, I'm using paper at the moment. We can imagine it's hard. I need to take a notch out of each corner. I need to know how big to make that, don't I? But for the moment, I'm just actually going to draw that little corner on. So I'm going to cut out a piece like this. And I'm going to cut out that same piece in all four corners. With me so far? So I cut those corners out, and then I fold up the remaining pieces. I left the flaps on there so I could, tape those in place. Like that. And get a box. So that's the process I'm going to go through. How do I figure out how big the box should be? I'm going to make a crappy picture of what we just did. I have my square sheet to start with. I cut out the corner. And then I fold here. To make a box. Since my goal is to find the box with the largest volume, what's the volume of this box? In general, if you have a box, what's the volume of the box? Exactly. Length times width times height. So somewhere on this box, I need to label what's the length, what's the width, what's the height. Which one's which? Is length going this way or this way? Okay. And this is the width, side to side. And then this will be the height from top to bottom. Great. I have no idea what those numbers are. But I know they came from over here. What do I know about this piece of cardboard that I started with? It's square and it's 3 foot. And one other thing. Cutouts are also squares. And they're all the same size. Because if they're not all the same size, my box is lopsided, right? So this is 3 feet to start with. So is this. And all of these corners are the same size. But do we know how big the corner is going to be that we cut out? So that's something we can decide on, right? We can change that, and that'll change something over here. That's a decision we get to make. How big should that corner be? Should it be really small or should it be pretty big? There is a smallest limit. What's the smallest amount we could cut out? What's the smallest amount I cut out? This is my box. I cut out nothing. The volume of my box is nothing. I just end up with a flat sheet, right? What's the biggest cutout I could make? But remember, I've got to make a cut from this side and a cut from this side. So if I cut 3 feet this way, I got a problem, don't I? Half of that, right? So 1.5 feet. So I know that whatever the cutout size is, it's some number between 0 and 1.5 feet. Let's give that a name. Let's give that variable the definition. We're going to let x be the size of the corner we cut. That means I cut x away from the right side and I cut x away from the left side. That's what gives me the little flap that I then get to fold. Okay, wait a second. My goal is to work with this volume over here. But if my goal is to work with this volume, and the only thing I know is about the size of the corner, I need to be able to write these in terms of x. So here's a question for you. This single stick, this edge that we've labeled W, where is that over here? Ah, it's this middle dotted line here, isn't it? And the L, that's this dotted line. Where's H? Aha, that's this part right here, isn't it? Because we folded that up, that became the height of our box. So this is h. Wait a minute. That's x. This width right here is the same as this right here. That's the size we chose. So now I know that h is equal to x. I should be able to do the same things or similar things with L and W. What is the value of W in terms of x? How much is left behind once I take those two corners away? That's how I got that little bit right there, right? I took the two corners and pulled them off. What's an algebraic expression you can give me for W?
W minus 2x. W minus 2x.
I want to write W in terms of X, right? So I can't have a W on the other side. So I need something over here that's not W, but I'm taking 2x away. From what? I am definitely taking away 2x. But what am I taking it away from? I have this x. I have this x. There's W. Because that's the whole side of the square that we started with, isn't it? I can do the same thing for the length. L is here. That's an x. That's an x. There's L. And that whole thing is 3 feet. Fabulous, wonderful, marvelous. I now have an expression for the volume of my box in terms of x. The thing I get to choose. Volume of the box is length times width times height. That's 3 minus 2x times 3 minus 2x times x. This is an absolutely wonderful expression, in my opinion, because this is a function of one variable. And my goal is to make this as big as possible. I am trying to find a maximum. And what's more, I have a limit on the x's I'm allowed to use. We said that x had to be between 0 and 1.5 feet. Okay, wait a minute. I'm going to write this like a problem you just turned in on the homework. My goal is to find the maximum box, maximum volume. Well, it's actually to find the dimensions that give me the maximum volume. So I need L, W, and H. But now I can think of this as trying to find a maximum on an interval. How do I do a maximum on an interval? Chapter 4, section 3. How do I find the maximum value on an interval? Do I need to give you your homework back so you can look at it? You did this for me. How do I find the maximum of a function on an interval? And do what with it? I need my critical numbers. I need to know where that's zero, where it does not exist. And then I make the little chart because I have an interval. I use the ends and I use the critical numbers. If I was doing the thing without an interval, yes, I could use the increasing and decreasing part. But at the moment, I have an interval. So I need to know between 0 and 1.5. So I don't have to worry about the whole thing. I only have to worry about that section, right? So I need to start with a derivative. So I think it's going to be easiest if I multiply this out. And then I can take its derivative without having to use some crazy chain rule or some product rule. I think we'll multiply this out. 3 times 3 is 9. 6x, another 6x. 2x times 2x is 4x squared. There's another x out there. So I get 9x minus 12x squared plus 4x cubed. You want to find a maximum? What's v prime of x? Say that again, Simon. Every one of those numbers has a factor of 3 in it. That's a polynomial, so it's never undefined. I only have to worry about where it's 0. So I either need to factor that or I need to use the quadratic formula. People get annoyed at me when I write this in this order, so I tend to end up writing it the other way around. Then it looks like a quadratic the way everybody thinks of it, with the x squared at the left as opposed to the right. Does that factor in a way you can factor it easily? If the answer to that question is no, you should use the quadratic formula. If the answer to that question is yes, you should factor this. But that's up to your algebra skills, not me. Yes. Because this does happen to factor, but if you didn't know that, that's fine. You do the quadratic formula and you get x equals to 3/2 and x equals to 1/2. Great, fabulous. Now what? Since I have a closed interval, I know that x is between 0 and 1.5. I take any of the critical numbers that are in that interval and the endpoints. And I plug them into v of x. I don't need to plug into v prime because I've got the closed interval. If I didn't have the closed interval, then I might need to do something different. But remember, we have our formula for v. 3 minus 2x times 3 minus 2x times x. So it's 3 minus 2x squared times x. If x is 0, then I'm going to get something multiplied by 0. That gives me a volume of 0. If x is 1.5, then this piece is going to be 0 squared times x. That's going to be 0. I hope 0.5 is a positive number. What do you get when you put in 0.5? I get 2. 3 minus 1 is 2 squared times a half. That's 2. That's our biggest value, right? Now that I've figured out where the maximum is and what x value makes it and what the maximum volume is, I need to go back and read the question again. What did the question actually ask me for? It said,
The dimension.
which means I need the length, the width, and the height, which I have not found yet. But I have the expressions for length and width and height in terms of x, so I can go back and find those. The box has dimensions. Two foot by 2 foot by 0.5 foot. Length, width, height. Now I could have started this entire process by drawing a bunch of pictures, making a bunch of these actual example boxes, and doing some construction to figure out what I think is the biggest, how big the corner should be. But now I don't have to. I know right away, if you want the biggest possible box you can make from a 3-foot square, you need to cut half-foot corners, 6-inch corners out of the sides. Do you see the game here? If I want to find the biggest or smallest something, I need to write that something as a function of one variable. Figure out what that one thing is that I have control over. and make it work. And once I write everything in terms of that one expression, I can use my derivatives to find the maximum or minimum. These don't have to be geometry problems. Problem number 61. A baseball team plays in a stadium that holds 55,000 spectators. When ticket prices are $10, the average attendance is 27,000. When ticket prices go down to $8, the average attendance is 33,000. Here's a business setting. Find a demand function, assuming it is linear. Demand. Okay, now I need a setting, business ideas, demands. When prices are high, very few people want to buy something. When prices are low, more people want to buy it. So if I think of my demand idea as relating the number of purchased and the price, then I can draw a line. Now, this is where I get to say, I don't like this setup, but I didn't invent it. I tend to think of you can determine a price, and then the number of units sold should depend on the price. But the business people tell me, no, 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 no. You think about what your sales targets are, and then you set the price accordingly. So they think of units as the independent variable and price as the dependent variable. So I've got a graph that looks like this with P on this side and X on this side. And when prices are high, demand will be low. And when prices are low, demand will be high. So I expect something that goes like that. My demand equation should look like this. Now, they told me two pieces of information. They told me that at a price of 10, we had 27,000 seats sold, and at a price of 8, we had 33,000 seats sold. And it asked me for a demand equation, and I quote, assuming it is linear. I need the equation of straight line. What do I need to find the equation of a straight line? Okay, but what do I have in this case? I got 2 points, right? I got 2 X's and 2 P's. That's 2 points. 2 points, I get a slope, then I can make the equation for my line. Perfect. Slope, change in price over change in X. So that's 2 over negative 6,000 or negative 1 over 3,000. There's my slope. And now I can use whichever point you want. Which point should I use, Jack? Okay. Y minus the y value equals slope x minus the x value. Negative 1 over 3,000 multiplied by the x. 27,000 divided by 3,000 is just 9. The thousands cancel. Oh, and negative makes that positive 9. When I move the 10 over, I get y equals negative 1 over 3,000 x plus 19. Hey, that makes sense, doesn't it? My slope is negative, like I wanted. Straight line, I got a maximum price at 19, and then it goes down from there. Okay. So I have now done what the first part of the problem asked me to. I have found a linear demand equation. Part B says, what price should I pick to sell the most tickets? Sorry, not to sell the most tickets, to bring in the most revenue. Now that means I need another equation that I don't currently have. I need a revenue equation. Uh-oh. How do I figure out revenue? How many of you have done fundraisers for a club or an event or something like that? You go out to buy candy bars, you're gonna sell candy bars, chocolate covered pretzels, whatever. You're selling t-shirts, I don't care. Revenue. Revenue is how much money you bring in. How do you define how much money you bring in? Say again? I need the product, right? I need how much did I sell? And how much was each one? Right? So if I'm selling t-shirts, I need to know how much each t-shirt is selling for, and I need to know how many I sold. If I'm selling tickets, I need to know how much each ticket costs and how many of them I sold.
So does that mean we're going to use the same equation?
With one extra piece. That up there, that equation is price. This is price based on the number I sell. Hey, wait a second. Those are exactly the two things I was thinking. This is price when I sell this many. And down here, the revenue is price times number sold. So I'm going to take the price from right here. Say that again. Times X. And that is an equation in just X, isn't it? And my goal is to find the maximum for this. Now I'm back to exactly where I was before. I've got an equation in one variable, find its maximum. There's just one difference. This time, I don't have an interval. There's no interval here. How do I find maximum or minimum? I got to do the same thing I did before. I got to find my. I got to take the derivative and then what?
Set it to 0.
Set it to 0. Now I think that might be easier if we multiply this out first. So if I go back up here and I multiply this out, I get minus 1 over 3,000 x squared plus 19x. Then I can take my derivative. And that's a polynomial. Derivative of x squared is 2x. I got the 2 in the x. Derivative of 19x is just 19. That's never undefined. The only thing I need to worry about is where it's equal to 0. What x value makes that 0? You have a calculator. Do not do this in your head. It's awkward in my head. You try and do this. It's not easy. Negative 2 over 3,000 x equals negative 19. So I multiply. I get x is 3,000 times 19 over 2. The negatives on both sides cancel, and I get exactly. So now I know my goal is to sell 28,500 tickets. Provided that this is a maximum. Uh-oh. That'll tell me how much money I bring in. But how do I know that's the biggest? I'll say again. And that tells me what? What does that negative 1 over 3,000 tell me? You're on it. That's the reason I'm going to use, but I need to know why I'm using it, Zion. You're on the right track. How do I know if I have a maximum or a minimum?
Goes from positive to negative.
What goes from positive to negative? So I could make a sign chart, but there's another test. That test that you just told me about tests the first derivative. And if it goes from positive to negative, then I'm going from up to down, that's a maximum. If it goes negative to positive, that's a minimum. But there's another test. It doesn't use the first derivative. And if the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. Hey, wait a minute. The second derivative is negative. Negative means concave down. When I have concave down and a horizontal tangent line, I must be at the top. Whew. I do have a maximum. Now, Zion, if I go back and look at the original R of X, what type of equation is that? Yeah, that's our revenue equation. But in terms of the powers, that's a quadratic, right? And quadratics are parabolas. And the negative 1 over 3,000 means that parabola goes down, concave down, right? So I get it in several different ways. And you're right, I could have made a sign chart and gone up, down, right? Perfect. It would have worked both ways. However, I haven't actually answered the question I was asked. Because the question asks me, not how many tickets will I sell, but how much will the tickets cost? What's the price for each ticket? Because I go back here and I get the price based on the number of tickets sold, don't I? Hot dang! Go ahead.
Also, help us get to finding out.
It would help me with, well, knowing this is a parabola, the price is in there, right? So if I knew the revenue and then I divided by this number, that would give me this same price, wouldn't it? So yes, that would give me the same value. If you figure out the actual revenue by going back to the original R of X, then you say, oh, but that was for all 28,500 tickets. So divide by 28.5, you'll get 9.5. Because that's our maximum point. That's our vertex on our parabola, isn't it? Okay. There are literally hundreds of different applications to play with here. For example, and I'm not going to do it, I'm just going to point you to the examples in the textbook. Here, we're going to make a can. The can needs to hold 1 liter. What is the smallest amount of material I need to make the can? Well, the material is the area of the side of the can and the top and the bottom. So I can think of this as 2 circles and a rectangle. Problem. The area of a circle is pi r squared. The area of a rectangle is length times width. Well, the width of that rectangle is the height of the can. The length of the rectangle is the circumference of the circle. That's why you'll notice they've cut right here and unrolled the circle a little bit. And the 2 pi r, that's our circumference. This has two variables in it, r and h. I need a formula that's only one variable. Well, what do I do now? Run screaming for the hills, the end of the world. No, it isn't. I know this can has to hold 1 liter. What is the volume of the cylinder?
Wow.
The volume will be 1 liter, yes. But what's the formula for the volume of the cylinder? 4/3 is first cube. A cylinder, it's the area of the bottom times the height. The area of the bottom is a circle. So when I do this, I have another equation. Pi r squared h is equal to 1. Or if I do it in milliliters, it's 1,000, right? And the reason I would choose milliliters is because a milliliter is a cubic centimeter, and then I can do r and h in centimeters. So I have pi r squared h equals 1,000. So notice I end up with two different sets of equations in this problem. I end up with the area equation, top and bottom, plus side, and the volume is 1 liter, 1,000 cubic centimeters. I have two equations and two variables. I can use the second equation to get rid of one of the variables in the first equation. If I take this equation, I can rewrite it. H is 1,000 over pi r squared, and I can put this in here. The result is a function that's all in R. And if I simplify that function, I get this, which is now a function in one variable and only one variable, which means I can take its derivative and I can find the R value that will give me the minimum amount of material needed. There's just one problem. This time, this function is undefined somewhere. It's undefined when R is 0. Because I got division right here, yes? I can't divide by 0, so I'm going to need to make my charts carefully. There is a place where the derivative will fail to exist, because there's a place where the function fails to exist. The rest of the math behind this is done in the second example in the textbook on page 339, 338. And when I actually do it, I will see that there is a minimum somewhere, and I can figure out what the radius is and what the corresponding height is. So quite frequently, there are multiple approaches to a problem. Now, the textbook is actually pretty sneaky about this and offers me another way to do this in example 2 on page 339, where they actually take the derivative two different ways. They take the derivative of A but they also take the derivative of the other equation. Like we're doing related rates. It's the same. The problem is in turning our setting into an equation. Once I have an equation, I can take a derivative. I can find my maximums and minimums on that equation, but I need to start with, can I get the equation? Problem number 16. A rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of the base is twice the width. Material for the base is $10 per square meter. Material for the sides is $6 a square meter. The bottom has to be pressure treated because it's going to sit on the ground. And if you don't treat it, the wood will rot. So we need to use pressure treated wood on the bottom. That's more expensive. Find the cost of materials for the cheapest such container. Because if you think about it, I could build a rectangle that was really long and very short. Or I could build a rectangle that was really small side to side and fairly tall, as long as it holds 10 cubic meters. Now, 10 cubic meters is not a small amount of stuff. 10 cubic meters is pretty damn big. What's my equation? I need a cost equation. Here's the information this problem gave me. The container, open top. I should write that down. Open top. So I don't have to worry about 5 sides. Even a crappy picture helps. So I'm going to draw a box with an open top. That's why I can see this, because I can see it through the top, but I can't see those because they're hidden behind the other walls. Now, the way I've labeled this, the way I've drawn this, this should be the length, and this should be the width. And this will be the height. But the reason I know that this is the length and this is the width is because it says here the length is twice the width. So whichever piece were to be longer, that's your length. Make sense? But if I know the length is twice the width, I can actually say right here that L is 2W. That's helpful. I need an expression for the cost. Because that's what this is all about. I want to find the cost of the cheapest possible box of materials. So how do I get cost? the bottom of the box is going to cost me $10 per square meter, right? So it's $10 times the area of the bottom. And then it's $6 times the area of the sides. So, in terms of the letters I have on that picture, what is the area of the bottom of this box?
2W squared.
Length times width, but length is 2W. So that's, I'll write it like that for the moment. 2W times W, so I know it's length times width. Plus 6 times. There are 4 sides. Front, back, left, right. The front and the back are the same, aren't they? It's a rectangular box, so whatever the area of the front is, the area of the back is the same size. What's the area of the front? Width by height. Front and back means there's 2 of them. 2 width height. Front / back. Plus left side, right side. Left side, right side, I don't care which one we're going to pick. We'll do 1 and then we'll multiply by 2. So how big is the right side? Length times height. There are 2 of them. 2W times H. Left, right. Great. So this is 20W squared plus 6 times 2WH and 2 times 2WH, that's 4, and 2, that's 6WH. That's 36 of them. Okay. Houston, we have a problem. Not a big problem, but it is a problem. Same problem I have with the cans. 2 letters. I have a W and an H. How the hell do I get rid of the second letter? I need another expression, some other equation. Using information I have not yet used up there, I hope, to tell me about a relationship between these variables. What piece of information is up there that I haven't used? Volume. I haven't used the volume at all, have I? Fumble. What's an expression for the volume of the box? But the length is twice the width, right? So I can write 10 is 2W squared H. If I divide both sides by 2, I get 5 is W squared H. And if I look back at my cost expression has an H in it, doesn't it? It's got W squared and W. So if I tried to get W all alone here, I'd need a square root. That's annoying. But if I get H all alone, 5 over W squared, I can put that up here. And then I get a cost expression that is all in terms of W. And now I have something I can take the derivative of. And since my goal is to find the minimum cost, I want to minimize this. And once I know the width, I can actually figure out what the cost is. Okay, Zion, this is the time when I actually need the cost, not the size of the box, right? So I know what the budget's going to be. See how, depending on the situation, one piece of information be more valuable than the other. In this case, what I actually want when all is said and done is how much did this cost? Now, I will be able to tell you what the length is, what the width is, what the height is. But my goal is to tell you what the cost is. And to make sure I know it's a minimum. Questions? Yesterday, I talked about the power to the field house, right? And I said, maybe it'll be cheaper to run the power cable through the air. Maybe it'll be cheaper to go underground. Here's a picture of a river. I want to get from point A to point B. Point A is 8 kilometers upstream from point B. The river is 3 kilometers across. It's a big river. I'm going to get in my boat and I'm going to row the boat across the river. I'm going to move downstream as I do that. Then I'm going to reach the other side. I'm going to get the boat out of the water. I'm going to row. I can row at 6 kilometers an hour. I can run at 8 kilometers an hour. Where should I aim so that my trip takes the smallest amount of time? If instead of time I use dollars, I'm going to dig under the water and then I'm going to dig alongside to lay my power cables. What's cheapest? That's the same problem. That's the exact same problem as figuring out how to run power down the field house. Remember, I talked about packing spheres, the smallest we could? There's my smallest packing idea. This uses a lot of space. This uses less space. See how the circles fit into the holes left in the other row? This fits more circles per box than this does. This pads them better, so if they're glass, this might be better. But if they're steel, this might be better. I'll get more per box. This same idea can be applied in dozens of different places. Related to that packing idea, that sphere idea, this will blow your mind. Do you think bumblebees do calculus? When honeybees make hives, they pack the honey into little cells. The cells have hexagons around them, but the cells themselves are circles. That pattern with the sphere packing is exactly the way honeybees make hives. But it's more because hives are three-dimensional. And that cell is actually thick. The bottom of this picture, that's the front of the honeybee cell. The back is this triangular prism pointed in to the wall of the hive. What they do is they build two of them, one for each side. In order to use the least amount of materials, they can change the angle at the top of that point. The angle that minimizes the amount of wax used to make a beehive is within 1/10 of 1% of the actual value the bees use. Calculus is everywhere, people. Everywhere. Okay, two things. I did jump a section. This is 4.7. We skipped 4.6 because 4.6 just talks about more graphing using technology. We already did 4.8. That was our Newton's method stuff, and that was on the last exam. So that means tomorrow I'm going to do chapter 4, section 9. And that's the end of chapter 4. And that's a lot of stuff. I think we should have an exam before we keep doing other stuff. So tomorrow is section 4.9. Monday is a question and answer day. The homework for 4.7 and 4.9 would therefore be due Wednesday. And that means our next exam is a week from today. The review sheet is already posted. Has been since Monday. I will see you all tomorrow. Have a wonderful rest of your day.